In the 20th century, we were warned multiple times that the sun is not a lamp hanging in the sky for our convenience, but a gigantic nuclear reactor churning within its own magnetic field. When Earth's magnetic field shakes, our civilization shakes with it. Let's go back to 1957-1958, the International Geophysical Year. That was when scientists around the world decided to coordinate serious measurements of Earth, and coincidentally, solar cycle 19 entered its maximum, one of the strongest cycles ever recorded. The geomagnetic storms of 1958 were intense enough to push the aurora farther south than usual, disrupt radio signals, and interrupt long-distance communications. At the same time, we had just launched Sputnik and begun placing our equipment in orbit. That meant, for the first time, the sun's plasma outbursts could directly impact human technology in space. When physicists talk about the strength of a geomagnetic storm, they use a number called Kp, ranging from 0 to 9. When Kp climbs to 8 or 9, it's not just pretty lights in Alaska. Auroras slide down to latitudes where people aren't used to seeing them. But that light is only the part you see. The part you don't see is the distortion of Earth's magnetic field, and every time the magnetic field changes rapidly, Faraday's law tells us something non-negotiable. Electric current will appear in every long conductor. In 1859, the longest conductor was the telegraph wire. By the 1980s, we had stretched copper and steel wires across entire continents, connecting giant power plants to cities, factories, and the computer systems gradually replacing paper records. During cycle 21, especially the period 1979-1982, we saw more strong storms. Observatories recorded heightened geomagnetic activity, oscillating radiation belts, and disrupted radio systems. Not the end of the world, not collapse, but a reminder. And what fascinates me is not the lights in the sky, but the fragility in our design. You see, the U.S. power grid in the 1980s was no longer a few isolated plants. It was a massive interconnected network spanning states, dependent on ultra-high voltage transformers weighing hundreds of tons. Those machines were not built with the idea that a star 150 million kilometers away could suddenly push current into their steel cores. They were designed to operate stably under familiar conditions. But nature has no obligation to be familiar. When Earth's magnetic field is distorted, induced currents flow along lines hundreds of miles long, sneaking into transformers, saturating the steel cores and heating them up. And in a civilization increasingly reliant on computers, telecommunications, and satellite navigation systems under test, electricity is not just convenience, it is the lifeblood. To bed 1859, when telegraph lines caught fire and society carried on. By the 1980s, we had tied our existence tightly to the stability of alternating current. You can turn off a lamp and be fine, but if you disrupt an interstate power grid for days, you don't just lose lights, you lose communications, coordination, the ability to operate the systems you built. This isn't meant to scare you, it's a pure consequence of physics. When the magnetic field changes, current appears. When current exceeds design limits, equipment fails. And the storms we saw in the 20th century, whether in 1958 or the early 1980s, still fall within what we call large. But large doesn't mean the largest. If you look at the historical record and how the sun behaves, you'll see that what we witnessed so far is only part of the spectrum of possibilities. And what makes me think is not what has happened, but what physics permits to happen. The storms we've seen, they're impressive, but they still aren't the biggest thing the sun has ever done. And every time we confront a major phenomenon, humans have a very familiar tendency. We want to turn it into a grand cycle. We like round numbers, periods stretching thousands of years, repeating patterns that sound profound and fateful. There's something reassuring about believing everything operates according to some enormous rhythm, but physics has no obligation to satisfy that need. The cycles we actually understand about the sun are not mystical numbers, but cycles with specific mechanisms behind them. The 11-year cycle, called the Schwabe cycle, was recognized when astronomers counted sunspots and saw them rise and fall in a relatively regular rhythm. Roughly every 11 years, activity peaks, then declines. But it's not a perfect clock. Some cycles are strong, some weak. behind it lies the motion of conductive plasma inside the sun, where differential rotation and convection create a gigantic magnetic dynamo. Then there's the 22-year Hale cycle, when the sun's global magnetic field reverses polarity. After two 11-year cycles, the magnetic structure returns to its original state. This isn't mysticism. It's a consequence of how a mass of plasma rotates and twists its own magnetic field. From the 1960s to the 1980s, scientists began looking beyond a few decades by analyzing carbon-14 in tree rings and beryllium-10 in ice cores. These isotopes reflect cosmic ray intensity and indirectly reveal past solar activity levels. That data shows long-term variations, periods of high activity and low ones like the Maunder minimum. But what it does not show is a perfectly ticking 12,000-year clock. If someone tells me there's a 12,000-year cycle, I would ask, what mechanism produces it? The sun's dynamo follows plasma physics equations. You have to show how those processes could generate a rhythm lasting 12 millennia. You can't just conclude there's a matching cycle because the data record spans 10 or 12,000 years. Science doesn't accept a number just because it's impressive. Science demands cause and effect. So far, there's no solid evidence in isotope data or dynamo theory for a regularly repeating 12,000-year cycle. That doesn't mean the sun can't produce rare events once every few millennia. It just means we shouldn't replace lack of understanding with a story that sounds good. If we want to understand what the sun can do, we must start with mechanisms, equations, real physics, not with the allure of big numbers. If we want to know how far the sun can go, we need to go back to 1859. On the morning of September 1 that year, an English astronomer named Richard Carrington was observing sunspots through his telescope when he saw two bright white streaks flare up on the surface. It was the first time in history a solar flare was directly observed by the human eye. Carrington could know he had just witnessed the starting signal for one of the strongest geomagnetic events ever to strike Earth. Only about 17 hours later, instead of the usual 2 to 4 days, the enormous plasma cloud ejected from the sun, what we now call a coronal mass ejection, slammed into the planet's magnetic field. Its speed was estimated at around 2,000 kilometers per second, and when it arrived, it didn't ask permission. Earth's magnetic field was so strongly compressed and distorted that compass needles swung wildly around the world. Auroras blazed not just at the poles, but slid down to Cuba, Colombia, and even Hawaii. Miners in the Rocky Mountains woke up in the middle of the night thinking dawn had come. But that light wasn't sunrise. It was the aftermath of a star 150 million kilometers away, dumping its energy into Earth's magnetosphere. The more remarkable part wasn't the colors in the sky, but what happened in the copper wires. The most complex electrical system in 1859 was the telegraph, with long lines stretched across continents and oceans. When Earth's magnetic field changed rapidly, Faraday's law told us an electric field would be induced in any closed loop. No hypothesis needed. It's an equation. Induced electromotive force is proportional to the rate of change of magnetic flux. As global flux varied violently, currents began flowing along the telegraph lines. Stations reported sparks flying, equipment catching fire, and in some cases, operators receiving shocks. There were reports that some telegraph systems could even continue sending signals after batteries were disconnected, because the induced current from the storm was strong enough to replace the normal power supply. If you want a vivid illustration of Faraday's law, that's it. A star alters a planet's magnetic field, and the planet responds with current in its conductors. Based on modern estimates from magnetometer data and historical reconstructions, the Deist index for the Carrington event is thought to have reached around 850 nanotesla, with some studies suggesting even lower. To put that in perspective, that's a level of magnetic compression many times greater than the typical storms we observed in the 20th century. But pause for a moment and ask the important question. In 1859, what was our civilization? No national power grid, no nuclear power plants, no computer control systems, just telegraphs and some mechanical systems. Society was disrupted, yes, but it didn't collapse. Now imagine that same level of magnetic variation happening in the 1980s. The United States had built the high-voltage grid stretching thousands of miles, connecting large generating plants to population and industrial centers. Those lines were far longer than 19th century telegraph wires, and that very length made them vulnerable to geomagnetically induced currents. When the magnetic field varies, induced voltages appear along long lines, driving current into the steel cores of ultra-high voltage transformers. Machines weighing hundreds of tons designed for stable alternating current, not the slow, persistent direct current produced by geomagnetic storm. When the steel cores saturate, they heat up, vibrate, and in the worst cases, suffer permanent damage. In the 1980s, we had mainframe computers coordinating finance, national telecommunications systems, and satellites beginning to become part of information infrastructure. Everything depended on electricity. Compared to 1859, we didn't just have more conductors, we had far more to lose. So when I say Carrington is the benchmark for extremity, I'm not saying it for drama. I'm saying it because it's a recorded physical benchmark, an observed flare, a CME arriving in 17 hours, auroras at unusually low latitudes, and currents strong enough to burn the air as most advanced technology. And if it happened once, nothing in plasma mechanics says it can't happen again. Carrington isn't legend, it's data. And when you place that data next to a civilization deeply dependent on the stability of Earth's magnetic field, you start to see why I say what we've witnessed so far is only the beginning of the story. In the 20th century, astronomers systematically tracked sunspot numbers and realized that this star's activity rises and falls in cycles of about 11 years. There are weak cycles and strong cycles. Cycle 19, peaking in 1957 to 1958, was one of the strongest ever recorded. The smoothed monthly sunspot number exceeded 200, an impressive figure if you're familiar with solar activity charts. It also coincided with the International Geophysical Year, and ironically, just as we began observing space more seriously, the sun entered one of its most dynamic phases. Strong flares, radio disruptions, fluctuations in radiation belts all appeared during that period. Then came solar cycle 21, running from roughly 1976 to 1986, also a relatively strong cycle, with maximum in the late 1970s and early 1980s. In those years, we recorded many large flares and significant geomagnetic storms. This shows a simple fact. The sun's activity doesn't stand still, it oscillates, and sometimes it oscillates strongly. But more interesting than the question, how long is the cycle, is the question, why are there cycles? That's where dynamo theory comes in. The sun isn't a solid body. It's a rotating sphere of plasma, and it rotates unevenly. The equator spins faster than the poles. This differential rotation, combined with enormous convective flows in the outer layers, stretches and twists magnetic field lines. You can picture the magnetic field as invisible rubber bands being pulled and twisted over time. When they twist tightly enough, they rise to the surface as sunspots, and when the magnetic structure becomes unstable, energy can be released suddenly as flares or coronal mass ejections. That's the basic mechanism, and it's sufficient to explain the 11-year cycle and why, after 2 cycles, the global field reverses in the 22-year cycle. But here's the key point. The sun's dynamo is not a precise mechanical clock. It is a nonlinear system where conductive plasma moves in a complex magnetic field. In such systems, chaos is not the exception but the feature. Small changes in initial conditions can lead to major differences in a cycle's peak strength. That's why solar cycle 19 was much stronger than some others, and why solar cycle 21, though strong, wasn't exactly like its predecessor. When scientists try to predict the strength of an upcoming cycle, they rely on dynamo models, historical data, and surface magnetic field observations. But models, no matter how sophisticated, are still approximations of a gigantic plasma system we can't touch directly, so predictions can be off. We might forecast a moderate cycle, and it turns out much stronger, or vice versa. This doesn't mean science has failed. It means we're dealing with a complex natural system where nonlinearity and chaos play major roles. When you understand that, you stop looking for a perfect cosmic clock and start accepting that there's a spectrum of possibilities. The solar cycle provides a rhythmic framework, but the intensity and details of each cycle can vary considerably. And if such a system once produced Carrington in the middle of a cycle, nothing in dynamo theory says it can't produce a similar event, or even a stronger one, in another cycle. It's precisely the combination of relatively regular rhythm and inherent chaos that makes the story fascinating, and also makes accurate prediction far more humble than we might wish. If you want to see a specific example of what a strong cycle can do in the modern world, you only need to look at the late 1950s, when solar cycle 19 reached its maximum. The period 1957 to 1958 stands out not just for the unusually high number of sunspots, but also for the series of powerful geomagnetic storms that came with it. This was the cycle with the highest amplitude ever recorded in the 20th century, with the smooth monthly sunspot number exceeding 200, a figure that indicates intense magnetic activity deep inside the sun. When large flares occurred in succession and plasma clouds were ejected from the corona toward Earth, magnetometers around the world began recording strong fluctuations. That meant the entire planetary magnetic field was being compressed and stretched like a gigantic rubber ball under the pressure of the solar wind. But you didn't need a magnetometer to know that. You could see it in the sky. Auroras appeared not only at the poles, but slid down to lower latitudes than normal, signaling that the ionosphere and magnetosphere were being violently stirred. Yet the spectacular part of the phenomenon wasn't the most important thing. What mattered was what happened to our technical systems. In the 1950s, high-frequency radio was the backbone of transoceanic and military communications. HF waves relied on the ionosphere to reflect and travel thousands of kilometers. When a strong geomagnetic storm hit, the ionosphere became over-ionized, chaotic, and as a result, signals were jammed, absorbed, or completely disappeared for periods of time. Radio stations recorded prolonged blackouts, and for those dependent on radio communications from commerce to defense, that was no small matter. Aviation was also affected. Long-haul flights relied on radio to maintain contact and coordination. When signals faded, pilots had to reroute or wait for conditions to stabilize. You could call it temporary disruption, but to me, it was a real-world test. Every time the sun ramped up its activity, it was checking how much our systems could withstand. And 1957 also marked another iconic event. Sputnik was launched into orbit. For the first time in history, we placed an artificial device in space, right in the environment where solar wind and charged particle radiation move freely. That changed how we had to think about solar storms. It was no longer just about magnetic fields in the atmosphere. Now high-energy particles could collide directly with electronic components and satellites, causing interference, degrading lifespan, or causing failures. As the number of communications and weather satellites grew in the 1960s and 1970s, our dependence on the stability of the space environment grew with it. Meanwhile, on the ground, the U.S. power grid was expanding and becoming more tightly interconnected. Large power plants were linked together by high-voltage lines stretching hundreds of miles, and ultra-high-voltage transformers became critical nodes in the entire system. These devices were designed for stable 60 Hz alternating current, not for the slow, persistent direct current caused by magnetic field variations. When the global magnetic field changed rapidly, induced voltages appeared along long lines, and those currents could drive the steel cores of transformers into saturation. When saturation occurs, temperature rises, vibrations appear, and the risk of failure is no longer hypothetical. The 1980s marked another step forward. Mainframe computers began coordinating financial transactions. Telecommunication systems became more complex, and the economy increasingly relied on the continuous operation of electricity and signals. We no longer used electricity just for lighting. We used it to store information, compute, control, and connect. The electric civilization was no longer a convenience. It was foundational infrastructure. So when I look back at solar cycle 19 and the strong storms of that period, I don't see just a high activity phase of a star. I see an early warning. It showed that the sun could reach energy levels sufficient to shake our technical systems, even when those systems were still relatively simple compared to today. And as the grid and technology continued to expand in the 1980s, every new line, Every new satellite, every new computer became an additional point of contact with the fluctuating space environment. The storms of the 1950s were not the absolute peak of the sun's capability. They were only proof that when activity increases, our systems respond accordingly. And if a strong cycle could disrupt radio, affect aviation, and challenge satellites right at the dawn of the space age, then the only logical thing is to ask, what will happen when our electric civilization becomes even denser and more dependent? When you look at how the US power grid developed in the 1970s and 1980s, you begin to see clearly why a Carrington-type event is no longer a 19th century story, but a present-day engineering problem. After World War II, electricity demand grew steadily, but by the 1970s we had built a true interstate interconnected system. Large generating plants in the Midwest could supply power to the East Coast. Hydroelectric sources in the Northwest could support neighboring states. The idea made perfect sense. The more interconnected, the more flexible and stable the system. But in physics, every solution often carries a consequence. Each high-voltage line stretching hundreds of miles is essentially a gigantic conductor sitting in Earth's magnetic field. And when that magnetic field varies rapidly due to a geomagnetic storm, those lines are no longer just carriers of 60 Hz alternating current. They become sites where geomagnetically induced voltages appear. Faraday's law doesn't care about the purpose of the conductor. If magnetic flux changes, an electromotive force appears. In strong storms, the induced electric field on the ground can reach levels sufficient to drive slow direct currents along long transmission lines. This current is not the kind the system was designed to handle. Engineers designed the grid to cope with load overloads, short circuits, lightning strikes, or mechanical failures, but not to withstand an electric field extending thousands of kilometers due to global planetary magnetic variations. At the heart of the entire system are the ultra-high voltage transformers. These are not small metal boxes. They are gigantic structures weighing 200 to 400 tons with multi-layer steel cores and dense copper windings. Each transformer is custom built for a specific voltage and power rating. Manufacturing time can stretch over many months, sometimes more than a year, because they must be designed, fabricated, and tested carefully. You can't just go to a store and buy a 345 kV transformer like buying a fuse. And when geomagnetically induced direct current sneaks into the system, it drives the transformer's steel core into saturation. When saturation occurs, the linear magnetic properties disappear, current surges suddenly, and heat generation in the windings spikes. If this persists, insulation can degrade, windings can fail, and the equipment may need complete replacement. What's noteworthy is that most of the original grid designs from the mid-20th century did not account for a Carrington-class event. When engineers calculated safety margins, they relied on recent historical data. No one in the 1950s designed systems assuming the global magnetic field could drop to levels equivalent to a dist of 150 nanotesla. And because the grid was built incrementally over decades, it has no simple off switch. The systems are interconnected to optimize performance, but that very interconnection can allow induced currents to spread over large areas. If a significant number of ultra-high voltage transformers fail simultaneously, the problem isn't just temporary power loss. The problem is that the replacement supply chain is extremely slow. There is no national stockpile of dozens of these gigantic devices ready for installation. Transporting a transformer weighing hundreds of tons requires specialized vehicles, suitable rail lines, and complex logistics planning. Meanwhile, modern society depends on electricity at an unprecedented level. Hospitals need power for life support equipment. Water systems need electric pumps. Telecommunications and financial computers need continuous supply. The electric civilization of the 1980s was no longer a convenience. It was basic infrastructure. And that's precisely why an extreme geomagnetic event today is not just an astronomical phenomenon. It is a comprehensive test of our design. I'm not saying every solar storm will lead to disaster. Most events cause only minor disruptions and the systems hold up. But when you combine three factors: a star capable of releasing enormous energy, a planet whose magnetic field can be distorted, and a gigantic power grid spanning thousands of miles, you have an interaction we cannot ignore. The key point is not fear. The key point is awareness. The power grid does not exist outside of nature. It sits within Earth's magnetic field, and Earth orbits an active star. If a Carrington-class event happened once in the recorded historical record, then physics allows it to happen again. The question is not whether Faraday's law works, it always works. The question is how prepared we are for a scenario that the original system design never accounted for. And if the power grid is the physical backbone of modern civilization, then in the 1980s, a new nervous system was growing on top of it, the computer systems and telecommunications networks. In the early days of the electric era, a power outage meant lights going out and mechanical machines stopping. But by the 1980s, a power outage could mean cutting off the flow of information. Mainframe computers in the data centers of banks, corporations, and government agencies processed millions of transactions and records every day. They didn't just store information, they coordinated economic activity. In 1971, NASDAQ began operating as the world's first electronic stock exchange. That meant instead of brokers shouting prices on the floor, data was transmitted through computer systems and telecommunications networks. Trading became electronic signals, and once you turn the economy into electronic signals, you become dependent on the stability of electricity and transmission systems. Time synchronization also became critical. Financial transactions required precise timestamps to determine buy-sell order, calculate interest, ensure fairness and transparency. Clocks in computer systems had to be synchronized over telecommunications networks. If power became unstable and networks were disrupted, that time chain could break. In the 1980s, we also saw the rapid expansion of long-distance telephone and data transmission systems. Copper and fiber optic cables began carrying not just voice but computer data. Every switching center, every signal repeater depended on continuous power. You might have backup generators, but you still needed an overall stable system to maintain synchronization. This created a subtle but profound shift. Civilization no longer depended on electricity just for physical operation, but for maintaining its information structure. Think about it simply. In the 19th century, if the telegraph was interrupted, information slowed down. In the 1980s, if computer and telecommunication systems were disrupted on a wide scale, you didn't just slow down. You lost the ability to coordinate at a national level. Banks couldn't confirm transactions. Airlines couldn't access reservation systems. Financial markets couldn't open normally. And all of this was tied to an unspoken assumption. The power would always be there. When we added more layers of technology on top of the grid, computers, networks, time synchronization systems, we were building an increasingly complex and sensitive structure. Each new layer increased efficiency, speed, productivity, but each layer also added a dependency point. If you look at the system as a physicist, you see an increasingly dense network of conductors, circuits, and processors, all sitting within the magnetic field of a planet that can be disturbed by a solar storm. This doesn't mean technology is a mistake. It means we must understand the physical environment in which technology exists. When a strong geomagnetic storm induces voltage noise on the grid, it's not just lights flickering. The entire information processing system can be affected. And because computers operate at low voltages with precise binary logic, they are far more sensitive than old mechanical systems. The 1980s marked the transition from an electromechanical economy to a digitized one. That brought unprecedented speed and power, but it also tied the stability of society to the stability of power and signals. When you look back at Carrington 1859, you see telegraph lines burning but society continuing. When you look at the 1980s, you see a network of finance, information, and coordination dependent on continuous electricity. And when you place all of that in the context of a star capable of causing global magnetic variations, you begin to understand that the question is not just whether conductors heat up. The question is what happens when your civilization is encoded into electric currents and clock pulses, and that current is interrupted by the same Faraday's law that burned the telegraph wires a century earlier. And if computers and the power grid are the visible parts of the electric civilization, then in the second half of the 20th century, we extended that structure beyond the atmosphere. Starting in the early 1960s, communication satellites began to change the way the world connected with itself. Intelsat was founded in 1964 with the goal of building a global information system based on geostationary orbit satellites. Instead of relying solely on undersea cables and high-frequency radio reflected through the ionosphere, we began transmitting signals directly through space. A satellite in geostationary orbit at about 36,000 kilometers high can see nearly one-third of Earth's surface. With just 3 satellites positioned correctly, you could create an almost global communications network. That was technically marvelous. But it also meant that our information infrastructure now depended on devices floating in an environment dominated by the solar wind and the planet's magnetic field. At the same time, NOAA began deploying weather satellites from the early 1960s, providing near real-time cloud images and storm systems. These satellites improved weather forecasting, saved lives, and optimized maritime and aviation traffic. But all of them operated in an environment we were only beginning to understand. The Van Allen radiation belts, discovered in 1958, surround Earth like 2 rings of trapped charged particles held by the magnetic field. Under normal conditions, satellites were designed to withstand a certain level of radiation. But when a solar storm occurred, the density and energy of particles in the belts could increase significantly. That could cause surface charging on the satellite, sudden discharges, or errors in semiconductor circuits. In the 1970s and 1980s, satellite operators recorded temporary anomalies coinciding with strong radiation events. And there was another phenomenon, solar proton events. When a large flare or CME accelerated high-energy protons, those particles could reach Earth's orbit in as little as tens of minutes to a few hours. High-energy protons could penetrate the satellite's shielding and interfere with internal electronics. A bit in memory could flip. A sensor could output bad data. For a single device, that might just be a glitch. But when you add constellations of communications, weather, and Earth observation satellites operating simultaneously, every strong radiation event became a simultaneous test. What's interesting is that we built these satellites assuming space was a quiet vacuum environment. But in reality, it's a dynamic plasma environment where magnetic fields and charged particles are constantly changing. In the 1980s, the number of satellites wasn't as high as in later decades, but it was enough for global infrastructure to start depending on them. Transoceanic communications, international television, meteorological data all began to pass through orbit. That meant a strong solar storm could not only induce currents on the ground, but could simultaneously disrupt or damage devices overhead. You have a 2-layer system, the power grid on the surface and the satellite network above, both within range of the same energy source. When you look at the big picture, one thing is clear. We extended our electric civilization from Earth's surface into near space, but we did not leave the physical environment of the sun. We simply brought our technology closer to the energy source capable of disrupting it. And if satellites are just machines enduring a radiation environment, humans are a completely different story. When we entered the Apollo era in the late 1960s and early 1970s, for the first time humans left the thick protective layer of the atmosphere and most of Earth's magnetic field to venture into deeper space. Throughout the Apollo program, scientists were particularly concerned about a phenomenon called solar proton events, bursts of high-energy protons accelerated by flares or coronal mass ejections. We were lucky. The Apollo missions did not encounter an extreme proton event while astronauts were en route to the moon or on its surface. But during that time, there were solar proton events recorded strong enough to catch the attention of space physicists. If a major event had occurred while astronauts were outside Earth's protective magnetosphere, the radiation dose they received could have spiked suddenly and significantly. Earth's magnetic field acts as a shield, deflecting most high-energy charged particles. But when you leave that shield, for example, on a lunar orbit or in interplanetary space, you no longer have that natural protection. High-energy protons can penetrate spacecraft hull materials and pass through biological tissue, causing ionization along their path. At low levels, it's a long-term cumulative risk. At high and sudden levels, it can be an acute problem. What makes solar proton events particularly noteworthy is their suddenness. A large flare can release electromagnetic radiation to Earth in about 8 minutes, the time it takes light to travel from the sun to us. High-energy protons can arrive afterward in tens of minutes to a few hours, depending on their energy and the magnetic field structure between the sun and Earth. That means warning time can be very limited. In low Earth orbit, astronauts are still somewhat protected by the magnetic field. But if they are outside that protected region, for example, on the way to the moon, their options are few. You cannot dodge a cloud of charged particles propagating along interplanetary magnetic field lines. You can only shelter behind thicker shielding in the spacecraft or wait for the storm to pass. The engineers who designed the Apollo spacecraft accounted for average radiation risks, but they also knew that an extreme proton event could put the crew in a dangerous situation. This reminds us that solar activity is not just a problem for conductors and microchips. It is also a biological problem. Radiation does not distinguish between a transistor and a cell. When the energy is high enough, it ionizes molecules, breaks chemical bonds, and leaves traces in living matter. In the 1980s, as plans for space stations and even deeper exploration were discussed, questions about space weather became more urgent. We could forecast flares reasonably well once they had occurred on the sun's surface. But accurately predicting the timing and intensity of a major solar proton event before it began remained a challenge. Warning time might be enough to order astronauts to seek shelter in the spacecraft, but not enough to change orbit or abort a mission. And once again we see the same pattern. A civilization expanding into space, bringing technology and humans along, but still dependent on the behavior of a cyclic star capable of sudden outbursts. When you put the ground-based power grid, orbiting satellites, and astronauts beyond the magnetosphere into the same picture, it becomes clear that the sun is not only the energy source for life, it is also the source of disturbances that can test our limits. And if we want to understand how far the sun could go in the past, we cannot just look at a few decades of telescope records or satellite data. We must seek Earth's natural recorders. One of the most important tools emerged in the 1940s when carbon-14 was discovered as a radioactive isotope formed in the atmosphere. Carbon-14 is produced when high-energy cosmic rays collide with nitrogen atoms in the upper atmosphere, turning them into radioactive carbon. This carbon is then absorbed by plants through photosynthesis and locked into the tree's growth rings. That means each annual tree ring records not only its age but also a chemical trace of the radiation environment at that time. From the mid-20th century, scientists began to realize that by measuring carbon-14 concentrations in ancient tree rings, they could infer variations in cosmic rays and indirectly levels of solar activity. When solar activity is strong, the solar wind and its magnetic field push cosmic rays away from the inner solar system, reducing the amount of carbon-14 formed on Earth. When activity is weak, more cosmic rays enter the atmosphere, and carbon-14 levels rise. By the 1960s, 1980s, dendrochronology, the science of studying tree rings, developed strongly. Researchers constructed continuous tree ring chronology spanning thousands of years by cross-matching living wood samples with ancient and fossilized wood. Each ring becomes a precise timestamp, and when combined with isotope analysis, it forms a long-term record of the radiation environment and indirectly of solar activity. At the same time, deep ice cores from Greenland and Antarctica were drilled, providing data on isotopes such as beryllium-10, also formed by cosmic rays. When you place these records side by side, you begin to see a much broader picture than a few 11-year cycles. You see centuries-long periods of unusually high solar activity and prolonged low periods, such as the Maunder minimum in the 17th century, when sunspots nearly vanished for decades. What's important here is that isotope records show the sun does not always oscillate gently around a fixed average. It has long-term high and low phases, and the amplitude of variation can be significant. In the 1980s, we were not yet aware of specific extreme events like the short spikes in carbon-14 discovered many decades later. But even with the data available then, it was clear that solar activity in deep history sometimes far exceeded what we had witnessed in the modern era. Analyses showed that the 20th century, especially the mid-century period, was one of the high-activity eras, but not the only one, and probably not the highest in the entire 10,000-year Holocene record. This has an important implication. When we talk about normal, we usually think of the last few decades, but for the sun, A few decades are just a small beat in a symphony spanning millennia. Isotope data show times in the past when cosmic ray shielding was significantly stronger, implying that the sun's magnetic field and activity may have reached states we have never directly observed with modern telescopes. And that means the sun's range of possibilities is broader than our direct experience. When you combine tree rings, ice cores, and dynamo theory, you get a picture in which the sun is a long-term dynamic system capable of shifting between different activity modes. There is no evidence for a perfectly regular 12,000-year clock, but there is clear evidence that its past activity included much stronger and longer variations than in recent cycles. And if Earth's natural records show that the sun was once more active than in modern times, then the only logical conclusion is to acknowledge that what we have observed in recent decades is not the upper limit of its physical capability. That does not mean something extreme will happen tomorrow. It simply means we should not judge a star's potential based on a very thin slice of history. When you look at ancient tree rings and deep ice layers, you are reading a record far longer than the lifespan of any electric civilization. And in that record, the sun appears as a system with far greater oscillation amplitude than our short-term memory allows. When looking at those millennia-long records, one question is almost unavoidable. Is Carrington really the upper limit of what the sun can do? Carrington is the most extreme event we have, direct instrumental and eyewitness records of, but it is only one data point in a much longer historical sequence. If isotope records show solar activity once varied more strongly than what we saw in the 20th century, then there is no physical reason we must believe Carrington is the absolute ceiling. In a non-linear plasma system like the sun, where magnetic field lines can twist, stretch, and suddenly reconnect, the spectrum of released energy has no clear line saying this is the end. Flares and CMEs follow a probability distribution, lots of small events, fewer larger ones, and very rare, extremely large one. But very rare does not mean impossible. When physicists statistically analyze flare sizes, they often find a distribution close to a power law, where probability decreases as energy increases, but does not drop abruptly to zero at any fixed threshold. That means, in principle, events larger than Carrington could exist, even if their frequency is so low it exceeds our short historical memory. Another important point is that we see no evidence for a fixed millennial scale cycle that forces these extreme events to appear on a predetermined schedule. There is no 12,000-year clock ticking down with steady clicks. Long-term variations in isotope records show high and low activity phases, but not a precise repeating rhythm like the second hand of a clock. This makes predicting extreme events much more difficult. If there were a fixed cycle, we could look at a calendar and say we're near the peak or we're at the bottom. But nature rarely operates in such convenient ways. Instead, we face a probabilistic system. The probability of a small flare in a given year is high. The probability of a Carrington-sized flare is much lower, and the probability of an even larger event may be so low we have never directly observed one. Yet low is not zero. In probability mathematics, an event with small but positive probability will occur if you wait long enough. The problem is that our electric civilization does not span tens of thousands of years. It exists only in a very thin slice of the sun's history. When you combine the short lifespan of modern infrastructure with the long-term capability of an active star, you realize we are assessing risk based on a limited data sample. Nature does not need to follow our schedule, does not need to give quarterly financial warnings, and does not need to wait until we feel ready. If magnetic conditions on the sun build up enough energy and reach an unstable configuration, release can occur regardless of which year of the cycle or which decade of human history we are in. This is not a gloomy prophecy. It is a cautious conclusion from the physics of nonlinear systems. In such a system, there are short timescales, 11-year cycles, and longer, less regular variations. There are moderate events we see relatively often, and extreme events we can only infer indirectly through chemical traces or statistical models. When asking about events larger than Carrington, the most honest thing we can say is possible but rare, no fixed schedule, low probability but not zero. That is the uncomfortable position between confidence and unease where science often stands. It forces us to think not in terms of it will definitely happen or it definitely won't, but in terms of risk management in a complex physical world. If we accept that the sun has had more active phases than modern times, and if we understand that the energy distribution of flares does not magically cut off at Carrington, then the reasonable question is not, could it be larger, but how prepared are we for that possibility? And that is the question an electric civilization, built over just a few recent generations, must face when placing itself under the light of a star that has been active for billions of years. Recognizing that extreme events can exist brings us to another uncomfortable issue. How far does our predictive capability really go? We can track sunspot numbers, measure surface magnetic fields, observe the corona with telescopes and satellites, but accurately predicting the exact timing and intensity of a major flare remains out of reach. When an active region on the sun becomes magnetically complex, we know the probability of a flare increases. We can say high likelihood or risk is rising, but we cannot point to a specific hour tomorrow and declare that a Carrington-class event will occur. The reason lies in the nature of the system. Dynamo theory gives us a conceptual framework for how the sun's magnetic field is generated and reverses polarity, but it is still an evolving model. We understand that differential rotation and convection generate and amplify magnetic fields, that field lines twist and rise, that magnetic reconnection can release enormous energy. However, the details of that energy buildup and instability are nonlinear and sensitive to initial conditions. In nonlinear systems, small changes can lead to very different outcomes, and this makes quantitative precise forecasting extremely difficult. We can simulate plasma on supercomputers, but models are always approximations of a gigantic system with many different spatial and temporal scales. In addition, our observations of the sun are still limited. Most of what we know comes from surface observations in the overlying atmosphere. We cannot look directly into the interior where energy is generated, nor can we directly measure the full three-dimensional internal magnetic structure. Techniques like heliosismology allow us to infer some properties of the interior through surface oscillations, but that remains indirect inference. When a flare occurs, we usually only see the final result of a preceding energy accumulation process. Like an earthquake, we may know where faults lie, that stress is building, but we cannot say exactly when rupture will happen. Moreover, the satellite data we rely on to monitor solar wind and radiation has only existed for a few decades. Compared to the sun's billions of years of life, a few decades of direct observation is an extremely short period. That means our statistics on extreme events are based on a limited data sample. When we say a Carrington-type event has a certain probability in a century, we are extrapolating from a relatively thin record. This does not make forecasting meaningless. It simply reminds us of the degree of uncertainty. Space weather forecast centers can detect a flare when it occurs and estimate a CME's arrival time at Earth based on measured speed. That gives us from tens of hours to a few days to prepare for CME impacts. But electromagnetic radiation from the flare arrives in about 8 minutes, and high-energy particles can arrive in tens of minutes. That warning window is enough for some precautionary measures, but not enough to alter the course of history. Thus, we are in an intermediate position. We understand the basic mechanisms. We have real-time monitoring capability, but we do not yet have accurate long-term prediction of extreme events. This is not a failure of science. It is the nature of studying a spontaneous high-complexity plasma system. By acknowledging this limit, we do not abandon forecasting efforts. We place them in the proper context. The sun is not a mechanical clock, and our predictions are not prophecies. They are estimates based on current understanding and available data. And in a world where electrical and space infrastructure increasingly depends on the stability of that environment, understanding the limits of prediction is no less important than improving the predictions themselves. The limits of prediction force us to do something else equally important. Think seriously about the consequences if a Carrington-class event occurred in the context of the 1980s. Not as a sensational story, but as a pure engineering problem. Let's start with the power grid. When a strong CME slams into Earth's magnetic field and causes rapid variation, the induced electric field on the ground can reach levels sufficient to generate slow direct currents along high-voltage transmission lines. These lines stretch hundreds of miles, sometimes east-west where the electric field gradient can be larger. Those geomagnetically induced currents enter ultra-high voltage transformers. If the current level is high enough and sustained, the steel core can become magnetically saturated, causing increased current, heating, and mechanical vibration. Some transformers may automatically trip to protect themselves, but in a strong, widespread event, not every piece of equipment can avoid damage. Imagine several major substations in different regions going offline simultaneously. That could lead to widespread power outages, not just in one city, but across multiple states. When the interstate grid becomes fragmented, load balancing becomes difficult. Power plants may have to disconnect from the system to protect themselves, making the situation worse. Widespread blackouts are not just about lights going out. Water pumping and wastewater treatment systems depend on electricity. Hospitals rely on backup generators, but generators need fuel and maintenance. Traffic control systems, traffic lights, elevators all depend on continuous power. If multiple regions lose power at once, mutual support capability decreases and recovery time can stretch out, especially if some large transformers suffer physical damage and require replacement. The manufacturing and transportation time for these hundreds of tense devices can be measured in months. Now add the telecommunications layer. In the 1980s, long-distance telephone and national data transmission systems depended on electronic switching centers and signal repeaters. These devices require stable power and temperature-controlled environments. Power loss can shut them down, even if the cables themselves are undamaged. At the same time, ionospheric disturbance from flares can degrade high-frequency radio communications in the early hours. That means both ground-based and radio communications can be affected. In this context, coordinating recovery becomes more complicated, because the very systems used for coordination may also be disrupted. Electronic financial systems, including NASDAQ and interbank payment networks, depend on mainframe computers and precise time synchronization. If power becomes unstable or networks are disrupted on a wide scale, transactions may have to be paused. Banks may be unable to confirm transfers. Markets may close temporarily to avoid chaos. The modern economy operates at high speed thanks to electronic signals. When those signals are cut, speed drops to near zero. In orbit, communications and weather satellites face heightened radiation environments. The Van Allen belts can be inflated by particle streams from a CME, increasing the density of high-energy particles in certain orbits. Accompanying solar proton events can cause bit flips in memory, trigger automatic safe modes, or in worst cases, damage sensitive components. If several satellites temporarily go offline or lose control, international transmission and accurate weather forecasting capability can degrade. This is not merely inconvenient, it affects air traffic coordination, maritime transport, and emergency response. This scenario is not the permanent collapse of society. Systems have redundancies, and engineers are not naive. Many devices have overcurrent protection. Many facilities have backup generators. But in a sufficiently strong and widespread event, those protective layers can be challenged simultaneously. When many interdependent systems are affected at once, cascading effects can prolong disruption beyond the duration of the storm itself. The key point here is not to predict doomsday, but to recognize that 1980s infrastructure was built primarily to handle internal risks and terrestrial natural disasters, not global magnetic variations at Carrington-class levels. The physics of the phenomenon has been understood since the 19th century. The question is how well we have integrated that understanding into design and response planning. If such an event occurred, the consequences could include widespread power outages lasting many days in some areas, telecommunications disruptions, temporary halts in financial trading, and satellite anomalies. Not the end of civilization, but certainly a severe test of its resilience. And when placed in the context of low but non-zero probability, thinking ahead and preparing is not pessimism. It is the only way for a mature electric civilization to live alongside an active star without the illusion that it is always gentle. The history of the 20th century was not silent before we began worrying about Carrington-class scenarios in the electronic age. On the contrary, it issued clear warnings multiple times. Solar cycle 19, peaking in 1957 to 1958, is still recorded as the strongest cycle of the 20th century, since we began systematically tracking sunspot numbers. The smooth monthly sunspot number exceeded 200, significantly higher than many cycles before and after. Large flares appeared frequently, and magnetometer stations around the world recorded deep variations in Earth's magnetic field. This was not just graphs rising on paper, it came with real impacts. During that maximum phase, many geomagnetic storms caused strong oscillations in the magnetosphere, increasing induced currents in the ground and in long conductors. High-frequency radio systems, then the backbone of transoceanic communications, were disrupted multiple times. HF waves depend on the ionosphere to reflect back to Earth, but when X-ray and ultraviolet radiation from flares surged, the ionosphere became over-ionized, altering wave propagation characteristics. The result was radio blackout signals severely degraded or completely lost for periods from minutes to hours. For military, maritime, and aviation systems, this was not just inconvenience. It was a reminder that global communications could be interrupted by the activity of a star. Moving into the 1960s, during subsequent high-activity periods, many solar proton events were recorded. These events suddenly increased the density of high-energy protons in near-Earth space. Radiation detectors on satellites and on the ground recorded abnormal increases, and some events were strong enough to affect satellite operations and sensitive electronic equipment. When high-energy protons entered the atmosphere, they could increase ionization at various altitudes, contributing to ionospheric instability. That in turn impacted radio systems again. Transpolar flight routes dependent on HF communications sometimes had to alter plans when ionospheric conditions became unfavorable. In the context of the Cold War, when fast and accurate information was a strategic factor, these disruptions could not be taken lightly. Scientists and engineers began to realize that space weather was not an abstract concept, but a real environmental factor that could interfere with technical infrastructure. Looking back at solar cycle 19 and the proton events of the 1960s, you see a repeated series of warnings. During high-activity phases, Earth's magnetic field is disturbed, the ionosphere fluctuates, and our most sensitive technical systems respond immediately. The 20th century did not witness an event surpassing Carrington in magnitude, but it clearly demonstrated the direct link between solar activity and technological disruption. Those events did not collapse society, but they traced the connection between astronomy and electronic infrastructure. They proved that when the sun ramps up activity, our systems do not stand aside. They participate in that interaction according to the laws of physics. If we regard Carrington as the benchmark for extremity, then solar cycle 19 and the 1960s solar proton events were lighter but clear warning bells, showing how the chain of cause and effect operates. These warnings were not intended to create apocalyptic visions, but to emphasize one reality. In the 20th century, even when the electric civilization was still relatively young, the sun tested it multiple times. Those warnings did not fall into a void. From the 1960s onward, and especially in the 1970s, 1980s, when power grids and satellites became more critical, engineers began to think seriously about mitigating geomagnetic storm risks. One major research direction focused on the central vulnerability of the system, ultra-high voltage transformers. Once it was understood that geomagnetically induced direct currents could drive steel cores into saturation and cause overheating, designers began considering shielding measures in the technical sense, not shielding from radiation as in spacecraft, but reducing the impact of unintended direct currents. Some ideas included improving core structures to withstand higher saturation levels, using materials with better magnetic properties, or installing direct current blocking devices at the connection points between lines and transformers. These devices act as filters, allowing normal alternating current to pass, while limiting slow direct currents caused by magnetic variations. These are not perfect solutions, but they represent a shift in thinking from viewing solar storms as distant astronomical phenomena to treating them as real design factors. Alongside this, the concept of redundancy was expanded. Instead of relying on a single transmission path, utilities increased the ability to reconfigure the grid when necessary. If one substation had to go offline, load could be shifted to another route, as long as the rest of the system remained stable. Dispatch centers became increasingly equipped with real-time monitoring systems to detect anomalies faster. In telecommunications and finance, data centers began to have independent backup power, including diesel generators and uninterruptible power supplies, to ensure continuous operation in case of grid failure. These steps do not eliminate risk from an extreme event, but they increase resilience and shorten recovery time. In parallel with infrastructure improvements, the field of space weather forecasting received more investment. Satellites observing the sun and solar wind provided near real-time data on flare activity and CME speeds. When a CME is detected and its speed measured, scientists can estimate its arrival time at Earth within tens of hours. This allows grid operators to prepare, for example, by reducing load on certain lines or monitoring transformer parameters more closely. Space weather forecast centers also issue warnings about solar proton events, so satellite and aviation operators can adjust plans as needed. Although we cannot yet accurately predict exactly when a major flare will occur, the ability to detect early and track its evolution has improved significantly compared to the mid-20th century. What is important here is the change in attitude. Instead of viewing solar activity as uncontrollable and therefore irrelevant, scientists and engineers began integrating this factor into design and operations. Transformer shielding, redundant design, and improved space forecasting are all responses grounded in physical understanding. They acknowledge that we cannot prevent the sun from erupting, but we can mitigate its impact on infrastructure. This is how a mature technical civilization responds to risk, not denial, not panic, but analysis of mechanisms and ways to increase system durability. Those improvements help us respond better, but they do not change a fundamental physical reality. The distance from the sun to Earth gives us only a limited degree of warning. When a major flare occurs, electromagnetic radiation, including X-rays and ultraviolet, travels at the speed of light. Light takes about 8 minutes to travel from the sun to Earth, and that means by the time we see the flare, the first radiation impact has almost arrived. There is no long lead time to prepare for this part of the event. High-frequency radio systems can degrade almost instantly due to sudden ionospheric ionization. Satellites can register increased radiation flux within minutes. This is not a gradual process. It is a rapid response bounded by the speed limit of the universe. The second part of the story, the coronal mass ejection, travels much slower than light but still fast enough to humble us. Depending on initial speed, a CME can reach Earth in anywhere from tens of hours to a few days. This provides a more useful warning window. When solar wind monitoring satellites detect a CME and measure its speed, scientists can estimate when it will collide with Earth's magnetic field. During that interval, grid operators can enhance monitoring, adjust network configurations, or prepare responses. Satellite operators can switch equipment to safe mode to minimize damage from high-energy particle fluxes. However, even with tens of hours, we cannot defend completely. There is no switch that can turn off the entire national grid for 2 days without causing consequences more severe than the storm itself. We cannot move all satellites out of orbit or wrap them in thicker shielding at the last minute. Systems are designed with a certain tolerance level, and warnings allow us to optimize responses within those limits, but they do not eliminate risk. Moreover, not all CMEs are the same. Their impact depends on the orientation of the internal magnetic field within the plasma cloud as it approaches Earth. If the southward magnetic component is strong and sustained, it can couple efficiently with Earth's magnetic field and cause larger geomagnetic storms. This component is often only accurately measured when the CME is near Earth, meaning the true severity may only be confirmed right before the strongest impact occurs. Thus, even with good warning systems, uncertainty remains. We may know a storm is coming, but its precise intensity may not be clear until too late to alter infrastructure configurations. This does not make warning systems useless. On the contrary, they are extremely valuable in mitigating damage. But they set clear limits on defensibility. The sun does not send weeks of advance notice, and its radiation does not wait for us to complete preparations. Warning systems are a tool, not an absolute shield. Understanding that helps us avoid two extremes. One is the illusion that technology has eliminated risk. The other is pessimism, that everything is futile. Reality lies in between. We can detect track and respond within a certain time frame, but we cannot completely eliminate our dependence on a dynamic cosmic environment. To truly understand why all of this can happen, we must go to the physical heart of the sun, into the nature of plasma and the process called magnetic reconnection. The sun is not an ordinary gas like the air around us. At temperatures of millions of degrees, matter exists in the plasma state, where atoms are stripped into positive ions and free electrons. Plasma is electrically conductive, and when a conducting medium moves in a magnetic field, the two become tightly coupled in what we call magnetic flux freezing. Magnetic field lines are effectively dragged along with the plasma motion. Now imagine the sun rotating unevenly. The equator spins faster than the poles. This differential rotation, combined with enormous convective flows in the outer layers, stretches and twists magnetic field lines like rubber bands being wound tighter over time. Those field lines can rise above the surface as sunspots, forming complex magnetic structures in the corona. Under normal conditions, magnetic energy accumulates gradually in these structures. The plasma is a nonlinear environment, and when magnetic configurations become too strained and tangled, they can suddenly restructure through a process called magnetic reconnection. Picture two bundles of magnetic field lines pointing in opposite directions and being pressed close together. In an ideal environment, they would not cross. But in real plasma, with finite resistivity and microscopic turbulence, the field lines can break and reconnect into a new configuration. When that happens, the energy stored in the magnetic structure is released in a very short time. That is the origin of a flare burst that releases energy equivalent to millions of nuclear bombs in just minutes. Magnetic reconnection is not an abstract concept. It is the mechanism that converts magnetic energy into kinetic, thermal, and radiative energy. Electrons and ions are accelerated to high speeds, emitting X-rays and gamma rays, and some plasma can be ejected outward as a coronal mass ejection. What is remarkable is that the energy is not created at the moment of the flare. It was already accumulated earlier in the twisted and stressed magnetic structure. The flare is only the moment of release. This explains why an active region can appear relatively stable for days and then suddenly erupt. When reconnection conditions reach the instability threshold, the system switches from slow accumulation to rapid release. For us on Earth, that sudden release can mean radiation arriving in 8 minutes and high-energy particles arriving in hours. For power grids and satellites, it means a gradual environmental change over days as the CME propagates through interplanetary space. It all begins with this fundamental physical process: plasma motion, twisted magnetic fields, and reconnection releasing energy. There is no intent, no hidden mystical cycle, only Maxwell's equations and plasma dynamics operating on a gigantic scale. When you understand magnetic reconnection, you see that extreme events are not magical exceptions, but a natural part of a system capable of accumulating and releasing magnetic energy. That does not make them less noteworthy, but it places them in the correct context. The sun is not angry. It simply obeys the physics of plasma and magnetic fields. When you look at magnetic reconnection from the perspective of equations and force fields, one thing becomes very clear. The sun has no intentions. It does not get angry, does not punish, does not warn us. Those words belong to human psychology, not to plasma. When field lines are twisted and stretched by differential rotation and convection, magnetic energy accumulates inevitably. When that structure becomes unstable and reconnection occurs, energy release is as inevitable as a compressed spring snapping back. There is no motive, no purpose, only the consequence of magnetic configuration and conducting fluid dynamics. We tend to anthropomorphize large phenomena because it makes storytelling easier. But if you truly want to understand risk and possibility, you must set aside emotional language and look at pure physics. The sun is a gigantic plasma ball, about 1.4 million kilometers in diameter, with a surface temperature of about 5,500 degrees Celsius and a core temperature of millions of degrees. It rotates, it convects, it generates and self-twists its own magnetic field. All of that happens continuously, without pause, without regard for human calendars. When magnetic fields twist strongly enough, magnetic reconnection releases energy. When energy is released, Radiation and charged particles propagate through space. If Earth lies in their path, we feel the consequences. That is the entire cause and effect chain. Nowhere in that chain is intent required. Understanding this does not diminish the seriousness of extreme events. On the contrary, it makes them clearer and more analyzable. If the sun acted on emotion, we could do nothing but hope for luck. But because it acts according to Maxwell's equations and plasma dynamics equations, we can study, model, and forecast to a certain degree. We can design systems with larger safety margins, build redundancies, and improve early warnings. Pure physics is not cold, it is neutral. It does not care whether a flare happens on a holiday or in the middle of a work week. It only reflects the state of the field and plasma at that moment. When I say the sun has no intentions, I am not downplaying the importance of what it can cause. I am placing it in the correct context. A star is neither enemy nor ally. It is a natural system. Our dependence on electricity, satellites, and computers does not change its nature. The only thing that changes is our level of sensitivity to variations that have always existed. Understanding that helps us avoid two extremes. One is viewing the sun as a conscious threat. The other is viewing it as completely harmless. It belongs to neither pole. It is a rotating, self-organizing plasma system following the laws of physics. Once we understand that the sun obeys only physics, not myth or destiny, the number 12,000 years begins to lose its allure. Humans are drawn to long cycles, vast periods that sound mysterious and fateful. A number like 12,000 years evokes the feeling that there is a cosmic clock ticking down, that we stand at a special point in history. But the truth is, we do not need that number to see the risk. Carrington in 1859 was enough to prove that the sun can produce an event strong enough to shake the technology of its era. We do not need a mystical multimillennial cycle to justify preparation. We only need to look at real data. Flares were observed. A CME arrived in 17 hours. Auroras spread to unusually low latitudes. Telegraph wires sparked and burned. That is not legend. That is recorded history. When an event has occurred once within the physical range of a system, there is no reason to rule out its happening again. No equation in dynamo theory says Carrington is the only event permitted in thousands of years. On the contrary, the energy distribution of flares shows that large events are rare, but not forbidden. The number 12,000 years, however psychologically appealing, can distract us from what is more important, the real possibility of a Carrington class or larger event within an undefined time frame. If you say an event occurs every 12,000 years, you inadvertently suggest we can calculate our position in the cycle and breathe easy, or panic accordingly. But there is no evidence for such a fixed cycle. There is evidence for long-term variations and for rare extreme events, but no steadily ticking cosmic clock. That means risk is not allocated according to human history. It is allocated according to plasma and magnetic field dynamics. Carrington happened without prior notice, and it could happen again in the same way. When you place this in the context of our electric civilization, the question is not, are we in the right 12,000th year? But how much can our infrastructure withstand if a similar event occurs during our lifetimes? Risk does not depend on how impressive the number sounds. It depends on physical mechanisms and our level of preparation. What has happened once in recorded history can fully happen again, because nothing fundamental in the sun's structure has changed since the 19th century. It still rotates, still convects, still twists magnetic fields, and still can reconnect. The number 12,000 years may make headlines more dramatic, but it is not necessary to understand the essence of the problem. The reality is simpler and far more serious. An active star once produced an extreme event sufficient to affect the primitive technology of the 19th century. We live in a civilization far more deeply dependent on electricity and electronics. When we set aside the fascination with big numbers and focus on what physics actually tells us, what remains is not panic, but the responsibility to understand. Understanding mechanisms is the first and most important step. If you know that flares originate from magnetic reconnection in plasma, that CMEs interact with Earth's magnetic field in measurable ways, and that induced currents obey Faraday's law without compromise, then you have a foundation for clear thinking rather than emotional reaction. When mechanisms are clear, you can ask the right questions. Which components of infrastructure are most sensitive? What are their tolerance thresholds? What is the real warning window? Those questions lead to the next step, investment in research. This does not only mean launching more sun-observing satellites. It means improving dynamo models, gaining deeper understanding of magnetic reconnection, and building more accurate plasma simulations. It also means studying specific impacts on power grids, satellites, telecommunication systems, and developing more resilient designs based on empirical data. Every small improvement in forecasting and design can significantly mitigate damage in a major event. But all of that only has value if it is done in a spirit of sobriety. Panic helps neither science nor engineering. Panic leads to hasty decisions, half measures, or exaggerated stories that distort the problem. Physics does not need drama, it needs precision. When looking at the history of solar storms, you see strong events, clear warnings, but you do not see evidence of inevitable destruction. You see a powerful natural system and a civilization learning to live with it. What matters is not predicting exactly which day the next major event will occur, because we cannot yet do that, but building systems with enough flexibility and redundancy to endure when it does. That requires investment in basic research, applied engineering, and public education to distinguish between real risk and myth. When we understand mechanisms, we are no longer obsessed with numbers like 12,000 years. We focus on probability, design, and resilience. A mature civilization does not avoid natural risks, nor does it amplify them into apocalyptic visions. It analyzes, measures, and prepares. The sun will continue to rotate and twist its magnetic fields regardless of what we think about it. The real question is whether we use our intelligence to understand and adapt, or to tell stories that frighten us. If we pull everything we have discussed together, the final question is not whether a 12,000-year number is real, but where we stand in the relationship between physics and our own civilization. Carrington in 1859 was not legend. An astronomer saw white light erupt on the sun's disk. 17 hours later, Earth's magnetic field shook. Auroras flooded to unusually low latitudes. Induced currents ran through telegraph wires, strong enough to make them spark. Placed in the context of 19th century technology, you see a simple system clearly impacted. Placed in the context of the 20th century with interstate power grids, hundreds of tense transformers, electronic telecommunications, and satellites, you begin to see a far more complex chain of interactions. We have also looked at the limits of prediction. Flares arrive almost instantly in 8 minutes of light. CMEs give us tens of hours, sometimes days. But true severity still depends on the internal magnetic structure of the plasma cloud, something we only measure accurately when it is very close. Dynamo theory provides a theoretical framework for how the sun generates and twists magnetic fields, but it is not yet a precise clock for every eruption. Plasma is a nonlinear environment, sensitive to initial conditions, and that means we can talk about rising or falling probabilities, but we cannot pinpoint the exact day and hour of the next extreme event. When you combine those two things, the historical precedent of Carrington and the current limits of forecasting, you reach a conclusion that is not dramatic but serious. Risk exists. It follows no fixed schedule, and it cannot be completely eliminated. This is where the distinction between probability and preparation becomes crucial. The probability of a Carrington-class event in any specific year may be low, but low does not mean zero. And when your systems have high dependence on electricity, time synchronization, satellites, and interconnected networks, even a small probability deserves consideration in long-term design. Preparation does not require belief that disaster is certain. It requires acknowledgement that nature does not adjust to financial calendars or political plans. Preparation means understanding magnetic reconnection mechanisms, investing in sun observation, improving models, and increasing infrastructure resilience. It means designing transformers with larger safety margins, building redundancies in telecommunications and finance, and using early warnings intelligently. When viewed through that lens, you are no longer swept up by sensational headlines, but focused on real engineering and scientific problems. Carrington gave us a concrete example of what the sun can do. strong cycles in the 20th century, and proton events gave us further evidence that the link between solar activity and technology is direct. Prediction limits remind us there is no absolute certainty, and probability, however small, does not automatically protect us. What remains is a choice of attitude, denial, panic, or understanding and preparation. I lean toward the last. The sun does not promise to be gentle with us. It only promises to obey physics. And our task is to understand that physics before it reminds us once again. If you want to continue exploring these big questions about the universe and the physics behind them with me, please subscribe to the channel so you don't miss the next conversations. See you in the next video. We still have so many interesting things to dissect together.